Today there are many satellites in orbit around the Earth. One of the most common types of orbits is circular, and for these satellites their motion represents uniform circular motion. Look at the figure of a satellite in a circular orbit about the Earth at a distance r from the Earth's center. To get the satellite in this position requires shooting it into space on a rocket that takes it up above the Earth's atmosphere and gives it enough speed so that as it falls toward the Earth due to the gravitational force, the Earth's surface curves away beneath it by exactly the same amount. Therefore, the satellite is always located the same distance above the surface. If we draw the free body diagram for the forces acting on the satellite, all we have is the satellite's weight due to the gravitational force. This force is a radial force, as it always points in toward the center of the circular motion. Therefore, we identify it as the centripetal force Fc equals big G times the mass of the satellite times the mass of the Earth divided by the distance between them squared. And we can always set the centripetal force equal to mv squared over r. We can now solve this for the speed of the satellite. This expression shows you that for every unique value of r, there is one and only one speed that corresponds to that orbit. If the satellite is orbiting closer to Earth, which means the r value is smaller, then the speed will have to increase in order to maintain that orbit. When solving problems, remember that r is the distance from the satellite to the center of the Earth, and not the distance above the Earth's surface. Notice that the mass of the satellite does not appear in the expression for its speed. Therefore, for a given orbit, a satellite with a very large mass will have the same orbital speed as a satellite with a small mass. However, it will take a lot more effort to put the larger mass satellite into orbit. Satellites are used for all kinds of applications, including telecommunications, research, and national defense. There are literally thousands of artificial satellites currently in orbit about the Earth. One network of 24 satellites allows for the increasingly important application of global positioning, or GPS. This system can determine the position of an object on the surface of the Earth to within 15 meters. The accuracy of smartphone GPS systems can be even better when coupled through their cellular network. We can talk about the period of satellite motion, which is just the time it takes for the satellite to complete one orbit. The speed of the satellite, which is equal to distance over time, can be written in terms of the period, where the distance for one period is equal to the circumference of the orbit, or 2 pi r. Therefore, the speed is equal to 2 pi r over t. We can substitute this result into the orbit equation we derived earlier and solve for the period. We find that the period is equal to 2 pi r to the 3 halves divided by the square root of the product of big G times the mass of the Earth. Although this expression was derived for circular orbits around the Earth, it also applies to orbits around any astronomical object. Take the motion of the planets around the Sun, for example. Their orbits are nearly circular, and we can calculate their periods by replacing m sub e with m sub s, the mass of the Sun. R would be the distance from the center of the planet to the center of the Sun. The fact that the period is proportional to the 3/2 power of the radius is known as Kepler's third law, which was discovered by Johannes Kepler in his study of planetary motion. Kepler's third law applies not only to circular orbits, but to elliptical ones as well. One final note on satellite motion is to consider satellites whose period matches the rotational period of the Earth, or 24 hours. This means the satellite would appear to remain fixed above the same point on the Earth's surface. Such a satellite is said to be in a geosynchronous orbit. This would have the distinct advantage of allowing for continuous communications between the satellite and a receiving station at a point on the surface of the Earth directly beneath it.